All right, perfect. So radiopharmacy, we're going to talk about how we produce the radiopharmaceuticals, and we're going to talk about the generator production and a lot of the quality control that we use. So there's two types of radioactivity. There's naturally occurring radioactive material and artificially produced. Nothing in nuclear medicine is naturally occurring. Everything is going to be artificially produced. So we can produce it in one of two ways. We can either produce it in a reactor, which means we're going to add a neutron, or we can produce it in an accelerator, which means we're going to add a proton. And if we add a neutron, that means we're going to make it neutron rich, which means a neutron is going to turn into a proton. Now, since this side is neutral and this side is positive, the only way to make this side neutral is to add something negative, which is a beta negative. So that means that things that are commercially produced in a reactor are going to decay by beta negative. Now, in an accelerator, I'm going to add a proton. And so a proton is going to turn into a neutron. This side's positive, this side's neutral. In order to make this side neutral, I need something positive, positive. So that's beta positive. So things made in an accelerator are going to decay by beta positive. And then the alternate decay pathway to beta positive, proton still turns into a neutron, but doesn't have enough energy to spontaneously do that. And so what I'm going to do is I'm going to add an electron, and that's electron capture. And all three of these collectively are known as isobaric transition because we're going from one isobar to another. The mass number stays the same. Generator is the third type. It's technically not a production method. We're just taking a radionuclide that was made in one of these three ways and putting it in a generator and waiting for the parent to decay into the daughter. All right, so when we add the proton or we add the neutron, something called transmutation occurs. And transformation is one of two things. Either it's transmutation or de-excitation. If you looked up transmutation in the dictionary, it really says element change. And so what we're doing is if we add a proton or we add a neutron, if the number of protons change, then it is transmutation. And on the converse side, once we make it proton rich or neutron rich, then it's going to decay, and it does that by transmutation as well. So in each one of these alpha, beta negative, beta positive, and electron capture, the number of protons change, so the element changes. Whereas in de-excitation, the element doesn't change. We either have gamma emission or internal conversion. The difference between gamma emission and internal conversion is gamma emission just means that the gamma ray leaves the nucleus. Internal conversion means on its way out, it hit one of its own electrons and caused a conversion electron. If it kicks out an electron through internal conversion, we call that conversion electron. And you can think of it as the nucleus internally converting its own energy to itself. So that gamma ray it produced converted its energy into its own electron and kicked it out. Okay, that doesn't happen often, but it happens every once in a while. So artificially produced radionuclides, they're going to be written in such a way that you have a target, you're going to add something, and something comes out. And we usually put that in parentheses. And what we add, or what is listed first, is what goes in. What's listed second is what comes out. And then we end up with the product. I'm going to skip ahead because I want to show you what that looks like before we get into anything else. Okay, so here's our target. It's oxygen 18. Oxygen has 8 protons in it. We're going to add the proton. So again, the first thing that's listed, what goes in, the second thing listed is what comes out. So we add a proton, so that means this 8 turns into 9. A neutron comes out, so that means the mass number, because 1 proton in, 1 neutron out, that's +1 -1. 18 plus 1 is 19. 19 minus 1 is 18, so that stays the same. And this is our product. That's what we want. So there's a couple different ways we can do this. Again, we can do this. Wrong way, Sybil. There we go. You're an accelerator. And specifically, there's 2 types of accelerators. We're going to use a cyclotron, and we're going to add a proton. Or through reactor production. And there's 2 types of reactor production, but both of them adds a neutron. Now, if we're going to add a proton, we have to speed it up. If we add a neutron, we have to slow it down. So those are opposite of each other. Why do we have to speed it up? Well, we're adding a proton to a nucleus that's positive. Two like charges, as you bring them closer together, this is distance, as you bring it closer together, repulsion increases. Until you get to a point where you're really, really close, then what happens is the nuclear force takes over and Coulomb force breaks down. Nuclear force is actually the strongest force in nature. So you have to get that proton with enough energy to get into the nucleus so it gets close enough to it. And if you can do that, then what happens is some of the energy that's housed in this nucleus escapes, and the particles that remain are missing energy, and that's what holds them together. So it's kind of like opposite thinking, but you can think of it like this. The nucleus is bound together so tightly because it's missing energy. The only way to break it apart is to add energy to it. Okay, so that's what the nuclear force is. So we're going to do that in a cyclotron. A cyclotron has two Ds, which is what you see here. These are Ds. And in the middle, we're going to have a particle source. And the particle that we're going to accelerate is actually going to be one proton and two electrons, meaning it has a -1 charge. So we call this a negative ion cyclotron. And the cyclotrons today are all negative ions. So since it has a charge, one of these sides is going to be positively charged and the other is going to be negative. And it's going to flip back and forth between positive and negative. It's going to be opposite on each side. So as it does that, the particle in the middle is going to be attracted to whatever side's positive and repelling from whatever side's negative. And as they're switching, it's going to go back and forth, gaining kinetic energy until it has enough energy. Right at the end, it's going to strip off the electrons, so only the proton hits the target. And when it hits the target, it has enough kinetic energy for it to be absorbed in the nucleus, and then it changes into a different element, and it's proton rich, or neutron deficient is actually the correct way of saying that. So we characterize our cyclotrons based on the amount of energy given to the particle that's being accelerated. So the more energy we can give that particle, the more different types of isotopes that can be created. Now, you don't need to know what energies create what isotopes, but just know that the cyclotrons are defined by the amount of energy that are given to the accelerated particle. Okay, so again, two types. Linear, that's what's going to be used in radiation therapy. They use linear accelerators. Cyclotron means circle, and a cyclotron today is about the size of a walk-in closet. So it's pretty big, but it's not as big as you might think. So again, things that are made in a cyclotron are going to be proton rich. So a proton is going to turn into a neutron, and it can either do that by capturing an electron, or it can do that spontaneously. And if it does that, then it's a positron emitter. So we're going to go through the electron capture ones first, and then we're going to go through the positron emitters. Now, you don't have to memorize this, but you do have to understand what's going on. So this is the target. This is the product. This is what's going in. This is what's coming out. So if I start with cadmium-112, which has 48 protons, and I like to do the protons first, if I add a proton, this 48 becomes 49. Since I changed the number of protons, my element changes. On the top, the 112, I add one proton minus two neutrons, because that's the mass number, that's the all number. 112 plus 1 is 113. 113 minus 2 is 111. That's how indium-111 is made. Indium-111 is used for white blood cell labeling and CSF imaging. All right, now your turn. Gallium-67. Which one is the target?
The 30 plus the 1 protons, and then minus 2. Minus 2 neutron.
Okay, yep. So 1 proton, 68 becomes 69. Minus 2 neutrons, 69 becomes 67.
And it becomes gallium.
Yes, yes. And which one is the product?
67, gallium-67.
Yes, very good. All right. All right, how about this one? Just explain this side here. What happens to this 81?
So proton at one proton, and then at -3 neutron.
Very good. Yeah. So 203 plus 1 is 204, minus 3 is 201. And then this is going to decay by electron capture. And I know it's electron capture because this 82 becomes 81, which means a proton turned into a neutron. And it did that by capturing an electron. So this number went down. This number stayed the same. All right. So this one's the confusing one. This is how I-123 is made. Again, you don't have to memorize this, just understand what's happening with the numbers. I'm going to start with xenon 54. I'm going to add a proton, so my 54 becomes 55. I add one proton minus 2 neutrons, so my 124 plus 1 is 125, minus 2 is 123. Turns into cesium 123. This decays by beta positive, which means that my mass number is going to stay the same because it's isobaric transition. My 55 is going to turn into 54 because a proton turned into a neutron, becomes xenon 123. And then this decays by electron capture. Now, just looking at this, I would not be able to tell if it's beta positive or electron capture because both of them, the numbers are going to be the same. Whereas a proton goes down by 1 and the mass number stays the same. So then ultimately we end up with I-123. And we can separate I-123 from xenon 123 because they're different elements. We use I-123 for a lot of things, uptake and scan, as well as ioflupane, DAT scan. All right, then we have our positron emitters. So positron emitters, what's going to be happening is we're going to add a proton and something's going to come out. So these are all the positron emitters that you need to know. We already went through this one. Proton in, so 8 turned to 9. Proton in, neutron out, 18 plus 1 is 19, 19 minus 1 is 18. Now, if a positron emitter is made with this reaction with one proton and one proton out, this target, when it decays right back to the target. Because when this decays, a proton's going to turn into a neutron, which is the opposite of what happened to create it. So F18, we use that for a lot of different things. All right, this one's the confusing one because this is an alpha particle. What's an alpha particle?
Plus 2 proton and plus 4 neutron.
It has 2 protons and 2 neutrons. That's why the mass number is 4. Yes, has a plus 2 charge. All right, so what's happening here? We've got 1 proton in, and the alpha particle is 2 protons out. So 7 plus 1 is 8. 8 minus 2 is 6. And on the top, we have 14 plus 1 minus 4. 14 plus 1 is 15. 15 minus 4 is 11. All right, now you explain this one to me. It's the exact same thing.
So I'm going to plus 2 protons and then minus 4 neutron. A proton.
Plus 1 minus 4 on top. What happens on bottom?
Bottom minus 1.
Plus 1, because that's what goes in. How many protons are in an alpha particle?
Minus 4.
Minus 2. Because an alpha particle has 2, 4. So 2 on the bottom, 4 on the top. So 8 plus 1 is 9. 9 minus 2 is 7. And then on the top, 16 plus 1 minus 4 is 13. Does that make sense? This is the number of protons. This is the total number of nucleons. So when I'm looking at this one, I'm only looking at the number of protons. So here, this is what goes in, plus 1. Alpha particle has 2 protons. That's what comes out, minus 2. 8 plus 1 is 9. 9 minus 2 is 7. And then on the top, I'm looking at protons and neutrons. So again, this is plus 1. Now this is going to be minus 4 because I'm including the neutrons as well. 16 plus 1 is 17. 17 minus 4 is 13. Okay. All right, let's do another easy one. What's happening here?
Plus 1 for proton and minus 1.
1 plus 1 minus 4 is 1. 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 1 min Okay, so that explains what is going on in the top, what's going on with the number of protons. Just plus one, right? Just plus one. Because when we're looking at this number down here, we don't care about the neutrons. That one's only looking at the protons, and so I added one proton. On the top, we're looking at the protons and the neutrons. And again, since this is a positron emitter made with this reaction, this is going to decay right back to this. All right. Gallium-68 can be made from zinc-68. This 30, adding one proton becomes 31. On the top, 68 plus 1 minus 1 stays the same. Now, we can make it this way because a lot of our radionuclides can be made in multiple ways, but commercially, it makes more sense to make it in a generator. Gallium-68, if you're asked how is gallium-68 made, it's made in a generator, okay? Because when you're asked these questions on your board exam, they're actually asking how is it commercially produced, knowing that it can be produced other ways, but commercially it's going to be made in a generator, which means we're going to make germanium-68, and germanium-68 is going to be made in a cyclotron, and germanium-68 then decays to gallium-68 via positron emission, via electron capture. All right, last one. Explain this one to me.
Plus one for protons and then a minus one for neutron.
Okay, so that number stays the same. Now what's happening with the protons?
I'm adding one.
Perfect. Perfect. All right. So now let's talk about nuclear reactor production. So now instead of adding a proton, we're going to add a neutron. Before I go to that, let me ask you a question. What did we have to do to the proton to get it into the nucleus?
Then electron.
We had to speed it up. We had to give it kinetic energy, right? We had to give it kinetic energy so it could overcome the Coulomb force and be gotten into the nucleus. With the neutron, we have to slow it down. So the proton, we speed it up. The neutron, we slow it down. Now, there's two ways that we can do this. We can do this fission or neutron activation. So we'll talk about fission first. So with fission, again, we're going to add a neutron, but we're going to slow the neutron down. How do we slow it down? We use moderators, and we call it a thermal neutron. So we slow the neutron down. It hits the fissionable nucleus. This fissionable nucleus is uranium-235. It's always uranium-235. When that happens, the nucleus elongates, and what we're doing is introducing distance within the nucleus. And we know that when we introduce distance, Coulomb force takes over and we have repulsion. Nuclear force breaks down. So when that happens, now all of a sudden, the nucleus is going to start repelling itself. And when it repels itself, it breaks apart. When it breaks apart, it doesn't need as many neutrons as it needed to hold it together, because when the nucleus comes together, it's really a weird phenomenon, because what's in the nucleus are protons and neutrons, and the protons are all repelling each other. The neutrons come in and hold it all together. So when this nucleus was broken into two smaller pieces, we didn't need as many neutrons. So we have extra neutrons. Then these neutrons go and hit more fission and produce more products. And the products they produce, I-131, Moly-99, Xenon-133, Cesium-137. What do all of these have in common? How do they decay? Beta negative, right? Because remember, if we add a neutron, we make it neutron rich. Neutron turns into a proton. This side's neutral, this side's positive, plus a beta negative. So now a negative and a positive equal a neutral. Add a neutron, beta negative. All of these are beta negative emitters. Okay, so these are the components that you want to know in a nuclear reactor. The fuel is uranium-235. The moderator, this is what's going to slow the neutrons down because we have to slow them down. The control rods, these are the control rods here. They go over the top of the fuel, and what they do is they absorb these excess neutrons. So they stop the process from happening. Because if you don't stop the process from happening, it's just going to keep going. And then you're going to have a lot of heat that's produced. And if your uranium is pure uranium-235, you'll have an explosion. And we don't want that. So the fuel causes the fission, it's uranium-235. Now in nature, uranium-235 is only 0.7%. The rest of it is uranium-238, which is quite abundant in nature. So you have a bunch of uranium-238, a whole lot of uranium-238, and then you just have a little bit of 235. So what we do is we enrich the uranium. And when we enrich the uranium, all we're doing is taking out the 238, which means the percentage of 235 goes up. So lowly enriched uranium, this is what we use to make our molybdenum and xenon and I-131. Lowly enriched uranium is less than 20% uranium-235. Highly enriched is between 20 and 90%. And then weapons grade, you have to have over 90% to be weapons grade. So even though we are using uranium-235 in our fission, it's not concentrated enough to produce an explosion. All right, these are all the fission produced products, all of these beta negative emitters. And you can't tell through the, like we did with cyclotron, like this many protons, this many neutrons. You can't do that with fission, but you can do that with neutron activation. Okay, with fission, you're just going to end up with these products. They're going to be different elements, so we can separate them out. With neutron activation, that means, again, we have a target. We're going to add a neutron. We have a product, and then the product is going to decay by beta negative. So this is still beta negative because we're adding a neutron. So also nuclear reactor, the neutrons come from the fission reaction. So these are still thermal neutrons, which means they're slow neutrons. So these are a little bit easier to understand because what's happening is we're going to have a neutron going in and a gamma ray going out. So that means that this number here, the atomic number, is not going to change because there's no protons there. And since the atomic number didn't change, the element doesn't change either. The only thing that changes is the mass number. So you've got lutetium-177 is made by lutetium-176. We add a neutron, gamma ray comes out, so we don't even count that, and it turns into 177. Same with samarium-153. Atomic number stays the same, element stays the same, this number changes, and iridium-92. Now, moly-99, I just said it was made by fission. It can also be made by neutron capture. So if we take moly-98, we add a neutron, that moly-98 becomes moly-99. But we don't like making it this way, and the reason is when you make it this way, not all of this moly-98 turns into moly-99. And so what that means is we have moly-99 over moly-98 plus moly-99. And what this is this is the equation for specific activity, not specific concentration. Specific concentration is millicuries per ml. I'm talking about specific activity. That is the radioactive isotope that you want over all of its isotopes. So this is, and this is not radionuclide purity either. So this is not moly over taq. Those are two different elements. This is moly-99 over moly-98 plus moly-99. And so if you make it this way, you've got some of that moly-98 contamination in it. You don't like that. So we don't like to make it this way, but we can. We can if we don't have any fission moly. Fission moly is pure. Okay, so the third way is generators. Generators, not really a production method. The parent is going to be made in a cyclotron or a reactor. All right. Have you ever milked a generator?
No.
Yeah, most of us haven't. So I don't know why we have to teach this, but we do. Okay. So inside of a generator, if this is the generator here, this is what it looks like on the outside. If we cut a hole in it, this is what it looks like on the inside. And this part right here is the column, which is what you see here. The column is made of alumina. The alumina forms a chemical bond with the molybdenum. Okay, whenever I say chemical bond, that means they're sharing electrons. So that chemical bond, the moly is going to stay in the alumina is going to stay in the generator, and everybody's happy. The moly is going to decay to technetium. Technetium has a different chemical structure, so it's going to fall off the column and it falls down to the bottom here because it's not bound to alumina. And then we just take our saline, we run our saline over it, we get our elution at the end. So how we milk the generator, it's very simple actually. It's such a simple design. We're going to put saline on here, and the saline vial will be punctured. There's two valves here. There's an air valve, and then there's the valve to go into the column. After we put the saline on, because we want to put that on first, then we're going to put the collection vial. And notice the collection vial is housed in lead because that is going to be where the technetium comes out. So the collection vial, the vial itself, is evacuated. And that means that all the air is pulled out of it. So when we put this on second, it's going to immediately suck things into its vial because it doesn't have any air in it. So it sucks the saline over the column and it pulls the technetium into the collection vials. Then you have this vial of technetium. All right, so I've given you all of the possible generators that are out there. The parent decays into the daughter. I've given you the parent, the half-life of the parent, how it's made, and how it decays. The daughter, the half-life of the daughter, and how it decays. You want to know this one, and this one. Those are the three that could possibly be on the exam. Okay, so let's talk about what happens with molybdenum. Molybdenum, 85 to 88% of the time, it's going to decay to Tech-99m, which is in a metastable state. Then it's going to give off that 140 keV gamma ray and turn into Tech-99. And we call that ground state because it's not stable. It's still radioactive, but it's in its ground state because it's got a super long half-life of beta negative. Now I said 85 to 88% of the time that happens. 12 to 15% of the time, the moly goes straight down to this ground state. And it doesn't do that. Either way, we end up here, and then we're going to decay by beta negative until we get down to ruthenium-99. All right, 3 tests we have to do on the generator. All right, with radionuclide impurity testing, what is the radionuclidic impurity that we're testing for?
The chromatography.
Okay, so that's going to be with the radiochemical impurity. The radionuclide impurity we're looking for is moly. We want to see if there's any moly. So with radionuclide impurity, you're looking for a radionuclide.
So it's divided by the Tech-99 on the bottom.
Yes, microcuries of moly per millicurie of Tech. Radiochemical, now again, chemical refers to the bond between two things that are held together by electrons. So radiochemical refers to the bond between the radiation and the ligand. So here we're testing for free Tech. And what's the other one?
Hydrolyzed reduced.
Yes, very good. And then the third one, chemical impurity. What chemical are we testing for? Aluminum. Yeah, because that's what the column is made of. If the alumina is positive, it's going to pull molybdenum with it because those two are bound together. So if it fails one, it's probably going to fail the other one. All right, so let's go through each of these. Radionuclidic impurity, we're looking for a radionuclide that's there that we don't want. So we're looking to see how many microcuries of moly per millicurie of Tech. All right, this is required after every elution. So it was changed for a short period of time where it was only required after the first elution. And I know there's some textbooks out there that say required after the first elution only. They changed it back. The answer is required after every elution. So how do we do this? We're going to take advantage of molybdenum having a high energy gamma and technetium having a low energy gamma. And we know with shielding, you need more shielding to stop high energy than low energy. So we're going to take this whole thing, put it inside of our shield. We'll put the lid on the shield, and we'll put that whole thing in the dose calibrator. The moly shield blocks the technetium. So all you get is the 740 and 780 keV gamma rays. That tells us how much moly there is. Then we take it out of the shield, and we measure, see how much technetium there is. We put it in this ratio, make sure you have less than 0.15 microcuries of moly per millicurie of tech at the time of administration. Okay, so the expiration time of the generator eluate is 12 hours. Once you make a kit, most of the kits, the expiration time is 6 hours. But if you just have it in its eluate form, it's going to be 12 hours unless it exceeds this limit before then. Why would that limit change? What's the half-life of molybdenum?
66 hours.
Okay. What's the half-life of technetium?
6 hours.
6 hours. Okay. So we're going to lose our technetium a lot faster than we're going to lose our molybdenum. So that means the denominator is going to go down. And if the denominator goes down, our ratio goes up. So over time, whatever this ratio is, it's going to continue to increase. And at some point, it's going to reach 0.15. And when it does, it expires. If it never reaches 0.15, then the expiration is 12 hours. So it's whatever comes first.
Mm-hmm.
All right. You have your calculator?
Can pull it up on the computer. Do I need to decay or just the standard?
All right. For this one, we're not going to decay.
Oh,
No. And if we do, I'll just give you the answer. So just a regular calculator is fine.
okay.
All right. What is the concentration of molybdenum in a vial that contains 300 millicuries of tech and 18 microcuries of moly? So how do I set this up?
So concentration will be C equal to activity over volume.
Okay, we don't have volume.
Oh.
We want to know how much moly we have in our technetium.
So we'll do 18 over 300.
Yes, 18 microcuries of moly over 300 millicuries of tech gives us our unit of microcuries of moly per millicurie of tech. It's like the only time you don't make sure the units are the same. All right, what's your answer?
0.06.
Perfect. Okay. And now over time, this number is going to go up. It's going to go up because your technetium is going to come down a lot faster than your moly is.
Okay.
All right. How about this one? We have a vial of generator eluate. It has 756 millicuries of tech. What is the maximum amount of moly we can have in this activity? How would you figure that out?
Will be X will be on top, and then 756 on the bottom equal to 0.15. 0.15.
I like to set it up as a conversion, but I think you're setting it up the same because I can have 0.15 microcuries of moly per millicurie of tech. All right.
113.4.
Excellent. Yes. All right. So that's radionuclidic impurity. We also do radionuclidic impurity on the strontium 82, rubidium 82 generator. And when we do that, it's still going to be microcuries of strontium 82 per millicurie of rubidium 82. So if you get a radionuclidic question about that, it's strontium 82 because strontium 82 decays into rubidium 82. It's going to be set up the same way. Okay, let's move into radiochemical purity testing. So now this is where we're looking for hydrolyzed reduced tech or free tech. How come we don't like hydrolyzed reduced tech? Where does it go?
It goes to the spleen, the liver, and
In
it's
the
like
bone marrow?
silver colloid.
Yeah. So since most of the reticuloendothelial cells are in the liver, we're going to see liver. It'll be hard to see spleen because it's only like 10 or 15%. So liver is what we're going to get. It's because it's insoluble, so it becomes phagocytized, and we're going to see the liver. For hydrolyzed reduce, the limit is 5%. We need less than 5%. All right, if there's free tech, what are we going to see?
Seeing the thyroid stomachs.
Thyroid, stomach, and salivary glands. All right, so here's how we do this. We're going to take a strip of paper, either silica gel or Whatman paper, and we're going to have a solvent in the bottom, and the solvent is going to be either saline or acetone. Put a dot of our tracer at the bottom, making sure the dot's not in the solvent because you want the solvent to go up the paper. And as it goes up, it separates the two components out. How far the solvent goes is called the solvent front. Down here is called the origin. We cut it in half, and then we count both of them and calculate our radionuclidic impurity. So the two impurities we're looking for is free tech and hydrolyzed reduce. As a rule, the free tech will be at the top because you can think of it as free to fly away. Hydrolyzed reduce will stay at the bottom. Think of it as being heavy. Heavy begins with an H, so does hydrolyzed reduced. All right, so let's do a problem. And let's say in this problem, we want to know what is the percentage of free tech. Okay, so I have free tech on the top, and I've got, just ignore the hydrolyzed reduce. I've got the tech MAA on the bottom. My top counts are here, my bottom counts are here. If I want to know the percentage of free tech, how do I set this up?
We have the total on the bottom,
Mm-hmm.
the top and bottom.
And what goes on the top?
The top will go on the top.
Exactly, yeah, because the top is the free tech. And if I want to know the percentage of free tech, whatever I want to know the percentage of, that goes in the top. All right, when you times that by 100,
1.26.
very good. We're going to call it 1%. So if I have 1% impurity, what is my percentage of purity?
99.
Got it. Yes. All right. We'll do 1 2-strip test and then we'll move on. All right. So in this one, Tech MDP, I've got hydrolyzed reduced at the bottom and I have Tech MDP at the top. And in my second strip, I've got Tech MDP at the bottom and I have free tech at the top. Here's my top of the strip counts, bottom of the strip counts, and this example has added the counts together for you. So in strip 1, I have to find hydrolyzed reduce. In strip 2, I have to find free tech. So let's do hydrolyzed reduce first. How do I set this up?
So it'll be 2530 on the top. And the total of 90530.
Very good.
That would be 12.8.
Okay. And then the free tech?
Okay, 1049 on the top and over 90599. 1.15.
Okay, we'll round it to 1.2%. All right, so if the question was, what is the percent radiochemical impurity? What would be the answer?
For number one.
For this is like the same
Oh.
test. It's a two-strip
Oh.
test.
So it'll be 2.8 and then 1.2 for
Right. So
impurity.
yes, we would add those together. So it'd be 4% impurity. And if the question was, what is the percent purity? What would the answer be?
So it'll be 96%.
You got it, 96%. Okay. I have a couple more problems. I'm just going to give you the answers to these, and you can go through and work on them yourself. But I think you've got it. So the percent purity here is 90.1. We can also do this with the activity. So instead of using the well counter, we can use the dose calibrator. This comes out to 98% purity. And this last one, this is 2% free tech, 4% hydrolyzed reduc, 94% purity. So when you get a chance, go back and work through those. All right, the last one, chemical purity. What's the chemical we're looking for?
Chemical. Aluminum.
Alumina, yes. What's the maximum amount of alumina that you can have?
Forgot. 10.
10 micrograms per ml, 10 micrograms per ml. So this is a commercialized kit that has this paper with a certain type of acid on it. And that acid, when it combines with alumina in this concentration, it does this. And then we put our sample next to it and see if it turns pink as well. So here is the sample, or the standard, I'm sorry, standard. So you can see that it turns the pink paper more pink. And then here is our dots. You just put a drop of your eluate on there, and if it doesn't turn pink, it passes. If it turns pink, that means that there is alumina in there. And if there's alumina in there, then there's probably molybdenum in there too, because the alumina and the molybdenum bind together. All right, let's do theoretical yield. So I think with theoretical yield, it's more important to understand what's going on in the generator than the calculations themselves. So we're going to do the calculations, but what's going on in the generator is you have the molybdenum that's decaying at a steady rate. And at any time, we can calculate how much molybdenum is there because no molybdenum is leaving the generator. The technetium leaves the generator, but not the molybdenum. The molybdenum is going to decay into the technetium, and then as it gets right about there, it decays at the same rate as the molybdenum. There will always be more molybdenum than technetium in the generator, and that goes back to only 88% of the moly decays to technetium. So you're never going to have more technetium than molybdenum. So in order to calculate how much technetium, because the theoretical yield is not the theoretical yield of the moly, it's the theoretical yield of the technetium. In order to calculate that, first we have to figure out how much moly do we have? And then we just multiply it by the ratio between the moly and the technetium, and that ratio will be given to you. So we have a Molytech generator, had 5,200 millicuries at calibration. We're going to elute it 20 hours later. What is the theoretical yield? And that 20-hour tech moly fraction is 0.83. So that fraction means that here at 20 hours, we've got 0.83 millicuries of technetium for every millicurie of molybdenum. All right, so what do you do first?
5,200 times 0.83.
Okay, we're going to take this number and we're going to decay it 20 hours. All right, I'm going to give you the answer to that because I don't think you have a scientific calculator. So that comes out to 4,222 millicuries of molybdenum. So now we know how much moly we have. How do I figure out how much tech I have?
So it decayed the tech by 20 hours.
We're not going to decay the tech. Our ratio, which means what we've figured out, is we've figured out this number, okay? That's 4,222. And I know the ratio here is 0.83. So that means all I have to do is take that number and multiply it by 0.83. And that gives me 3,505 millicuries of tech. So step one, find out how much moly you have. Again, it's more important to understand what's going on in the generator. We're going to find out how much moly we have, and then whatever our ratio is, we're just going to multiply it by our ratio, because that ratio is going to change over time. Over time, our ratio is going to get higher because I have more technetium compared to what I have with molybdenum. Once I get over here, that ratio stays the same. All right. We'll do one more, then we'll move on. We have a Molytech generator, has 750 millicuries when it was last diluted at 0600, which means we took all the technetium out. So we're starting over. We want to know how much tech is present at 1400, which is 8 hours later. Our ratio is 0.537. So first step, I have to decay this for 8 hours. So I do my decay equation. And I end up with 690 millicuries of molybdenum. Once I know how much moly I have, I just multiply it by the ratio. 0.537, and I have 371 millicuries of tech. So that's the theoretical year. That's when you're in the radiopharmacy and you have 6 different generators and you're like, I need 300 millicuries of technetium. Which generator am I going to use? So I'm going to calculate the theoretical yield of all of them. And that's which one I'm going to milk. The actual yield is what I actually get. And so that's going to be the theoretical yield, what you think is in there, times the efficiency, times the percentage that you can get out. And likewise, the efficiency is what you actually get divided by how much is in there. So these problems are a little bit easier. What is the actual yield if your generator has a 92% efficiency and the theoretical yield is 750 millicuries? How would you figure that out?
Multiply by 0.92.
Yes, very good. And so that comes out to 690 millicuries. All right, let's do this the other way. You eluted your generator. It had a theoretical yield of 550 millicuries, but you only got 475 out of it. What's your elution efficiency?
550 divided by 475. No.
If you did that, it's going to be over 100%. Your elution efficiency will always be less than 100%. So it's 475 over 550. Okay, so it's always going to be the smaller number on top.
Okay. 86%.
Yes, very good. All right, this one puts it all together. I'm going to go ahead and give you the answer, and you can work through it on your own time. Because I did I do this? No. Okay, so it comes out to 1,524 millicuries of tech. If you get stuck, send me an email, I'll walk you through it. All right, we're going to do a couple other calculations, and then we're going to move on to quizzing you, because that's my favorite part of the day. All right, we have a vial of 115 millicuries of tech-mebrofenin. It's in 10 ml. You need a dose of 5 millicuries. What volume do you draw it? What do you do?
I would 115 on the top over X equal to 115 over 5 equal to 10 over 6. Is it 0.43?
It is. Yes, very good. All right. All right, let's do another one just to make sure. You have a vial of 100 millicuries of Tech MDP and 7 ml. You need a 22 millicurie dose and a 12 millicurie dose. What's the volume for each one?
The first one is 1.454. The second one is 0.84.
Yes, excellent job. All right. I think I'm going to skip this one, go to this one. I'll actually tell you the answers to this one. This one is you need a dose now at 1 o'clock and 2 o'clock. Your answers are going to be 0.6, 0.7, and 0.8. So work on that when you get a chance. Let's do this one together. You have a vial of 120 millicuries of Tech DTPA in 6 mLs. You need a 10 millicurie dose now and a 10 millicurie dose in 2 hours. What I want you to do is don't worry about the 10 millicurie dose now. I want to know this 10 millicurie dose in 2 hours, what is the volume?
So the decay 10 millicurie first. Decay 120 first.
You don't have a scientific calculator, do you?
No, I don't.
Okay, so the 120 millicuries decayed for 2 hours becomes 95.2 millicuries.
Point 4.76.
Should be 0.63 mLs. So
yes.
Yeah, so now you have 95.2 millicuries in 6 ml.
I put 120.
Okay, all right. Well, that would do it. All right. This one I'm going to give you the answer for. This is the total activity you need to put in this kit to make these doses. The answer is 143. And we'll go ahead and work through this one together. Okay. So we have Tech DTPA at 6 a.m. and we need an 8 a.m. dose for 40 millicuries. The easiest way to do this is to use our decay factors. So 1 hour decay factor of technetium is 0.891. And if I need 40 millicuries 2 hours later, I know that I need more at 6 a.m. because it's going to decay by the time 8 a.m. comes around. So I'm going to take that 40 millicuries and I'm going to divide that by my 1 hour decay factor. And since it's 2 hours, I'm just going to square it. When I put that in the calculator, it's 50.4. So this first one is 50.4. Now the second one, I need 7 millicuries at 9 a.m. I'm going to take 7 millicuries. I'm going to divide it by that 1 hour decay factor again. But since it's 3 hours between 6 a.m. and 9 a.m., I'm going to put it to the third. And that's going to come out to 9.9. So this one's 9.9. We'll do the same thing, 20 millicuries. Now I have 4 hours that has elapsed. And this one comes out to 31.7. And the last one comes out to 71.2. So you just add all those together, And that's the total activity you need to put in that kit at 6 a.m. to get all of these different doses. All right, that was the last slide. What questions do you have?
I think the physics part, the first part of the lesson is really hard. I have to go over it again and again.
Yeah, it's important to remember the top is the mass number. That's the A. A, you think of it as standing for all, so that's protons and neutrons. And the bottom number is just the protons. And I feel like you got the top number because you're like, okay, plus this, minus this. But the bottom, think of the bottom, it's just the number of protons. All right, here's our questions. If I am making something in a cyclotron, and am I adding a proton or a neutron?
And it
Making something in a cyclotron, do I add a proton or do I add a neutron?
add proton.
Proton, yes, yes. And what do I have to do to the proton to get it into the nucleus?
With the electron.
You have to speed it up. You have to speed it up, yes, which is opposite for a reactor, which you slow down the neutron. If I make something in a reactor by adding a neutron, how is it going to decay?
Add something into the, I'm sorry,
Is it going to decay beta positive, electron capture, or beta negative?
beta, for a cyclotron,
No, for a reactor.
or reactor, beta minus.
Very good. Yes, beta minus. All right. Let's talk about what is the fuel used in fission? So a neutron hits the fissionable nucleus. What is that fissionable nucleus? That one is uranium, uranium-235. It's always uranium-235. Yeah. Okay. What is the purpose of the control rods in the reactor?
I don't know.
All right. That one is to absorb the neutrons, absorb the neutrons. All right. So, what percentage of molybdenum decays to Tech-99m?
88.
Okay, 85 to 88. It's anywhere in between those. Okay. All right. If I'm looking for how much moly is in my tech, is that radionuclide impurity or radiochemical impurity?
Radiochemical.
That one's radionuclide because moly is a radionuclide. So I'm looking for the impurity of the moly. What are the two radiochemical impurities that I test with radiochemical impurity testing?
3 tech and HR.
Very good. And what is the chemical I look for in chemical impurity testing?
Molly minus.
No, alumina. Chemical is not radioactive. That's going to be alumina. All right, for radionuclide impurity testing, where we're testing for the molybdenum, what's the maximum amount of molybdenum you can have?
0.15.
0.15, what's the unit?
You micro Q
Uh-huh.
curly.
Microcurie of moly per
ML.
millicurie of tech. Microcurie of moly per millicurie of tech. So you'll have your microcuries of moly on top, millicuries of tech on the bottom. Okay. All right. What's the maximum amount of hydrolyzed reduced tech you can have in your dose?
A 10.
5. That one's 5%. 5% of hydrolyzed reduced. And if you have hydrolyzed reduced in your dose, where does it accumulate?
In the column.
In the liver. In the liver.
Yeah.
Yes, the liver. But if you have free tech, where does the free tech go?
Free tech go to the salivary gland,
Mm-hmm.
the stomach.
And one more. And right here. Right here. The thyroid, right? The thyroid. Yeah, yeah. All right. Excellent job. I'm going to stop recording.